Hello and welcome back to the Data Unite channel. Today we will implement the linear regression model using Python, and I will use Jupyter notebooks for the creation of the script, and the aim is to build a model which predicts sales based on the money spent on different platforms such as TV, radio and newspaper for marketing. So in order to do this, first we need to import the needed libraries. So we'll import pandas, numpy, matplotlib and seaborn. Okay, this should be code. After this, we need also to read the dataset. So first we need to read the file that is gonna be create our dataset. So we do it like this. And then if we want to see some value, so some of the rows that we have into our dataset, we can just call the following function, which is the following command, which will show us the top 5 values from our dataset. And also it's important for us to know the shape of our dataset. So we know that we have 4 columns, but how many rows do we have? We'll do it like this. And this shows that we have 200 rows and we have 4 columns. Now it is also important for us to know if there are some missing values or duplicate rows, or also to check if there are some outliers. So let's check the following. First of all, check for missing values. Since we have all zeros, this means that none of the columns have missing or null values. Now we can continue to checking for duplicated rows. So we have false. This means that we don't have any duplicated rows. And for checking about the outliers, we need to build a figure which will have 3 subplots. Each subplot is gonna be for each of the independent variables. Our dependent variable is sales. This is the one that we want to predict. And these are the independent variables which are provided to us. And for that we do the following. So we do figure we'll have 3 subplots, and the size of the figure is gonna be 5 by 5. Then we will create the 3 plots. So plot 1 is gonna be a box plot, which will give us the mean, the 25 percentile, the 75 percentile, the 0 and 100 percentiles of that specific feature. I'm gonna repeat the same for each of them. Okay, I have a typo because the axis should be 2. Okay, so we can see that we have some outliers into the... Why I don't have the names of... I forgot to print the layout. Okay, now we have the names of each independent variable under the graph. So we have for TV, there are no outliers. For radio, there are no outliers. But for newspaper, we have, from what I can see, 2 outliers, which is not a lot, so we can continue. This is not gonna impact on our results anyway. And now we want also to know the distribution of the dependent variables. So we want to know the distribution of the values in the dependent variable, which is sales. And for that, we will create a new graph, which will show us how is the distribution of the data. So it's going to be a Seaborn plot. And from this graph, we can see that the data is almost normally distributed because we have shape similar to a bell. So it's the normal distribution is also known as a Gaussian distribution. So it is the same. The most important part is that this distribution has this sort of form or figure. Now we want to know how much if each of the independent variables are correlated to our dependent variables. So we want to know the correlation and this we can show it in 2 ways. One is to create a pair plot, a scatter plot, which will show us how with increasing of one value, what does the other one do. So is it the increasing, decreasing, or does it stay in the same place? And the other way is to create a heat map that will show us the coefficient of correlation between the 2 variables. So first, let's make the first one, which will give us the visual perspective to see how the data moves when increasing one variable into the other variable. So we do it like this. It's gonna be a pair plot because we use 2 variables. So we have one variable which is sales, and the other one is gonna be one of the 3 independent variables. So as an input is our data set, and then we have 3 variables for the x-axis, which are TV, radio, and this should be a comma, and then one y variables is just sales, the height of the figure is gonna be 4 units, and the aspect is gonna be 1. This is the aspect ratio of height and width of the figure, and we want scatter plot. Okay, this is a typo, pair plot. Okay, so we can see that if we increase the money spent into TV marketing, we see also increase of sales. But for radio and newspaper, we cannot say this, because for newspaper, there is no difference. And in radio, there is some difference, but we are not that sure, because we see that you increase the money spent into marketing in radio, we have some increase, but not that significant. So since we are not sure, but this is a good visual way to understand the correlation between the variables with the dependent variables, so with sales. Now we can make it also more clear with using the heat map plot that's gonna give us the index. So that's gonna be the coefficient of the correlation between the variables. So we do it like the following way. Okay, so we see on the left and on the bottom side of the graph, we see the names of the features, of the columns. Our dependent feature is sales, and independent features are TV, radio, and newspaper. And you can see that into this graph, each feature, this graph shows the correlation between each feature with every other feature. So we have 12 entries because we have this is 16 entries, so we have 4 by 4 matrix. And from this heat map, we can see that the correlation between sales and TV is 0.9. This means that they are correlated 90% of the time. Whereas we can check newspaper with sales is 0.16, which is 16% of the time, because this value here ranges from 0 to 1. So the closer to 1, the more correlated the value is, the variables are. So because we can see sales is 100% correlated with sales. So in our case, would make sense, the biggest sense, if we use TV marketing in order to predict the sales of our product. So having this information that we had seen until now, we can start building our model. And we can build two types of models for the linear regression. One is the simple linear regression, which takes only one independent variable and one dependent variable. And one is the multiple linear regression, which takes multiple independent variables and one dependent variable. So in our case, we will first start by building the simple linear regression model. And for that, the formula for this type of model is the following: y equals y, which is the dependent variable, equals to a plus b times x, which is the independent variable, plus some error. We will assume that in our case we don't have errors, so we can eliminate this part. And a is the value of the intercept. So it's gonna be the intercept of the regression line. And b is the slope. And in our case, the formula will be the following. Sales equals A plus B multiplied by the value of the of TV. So multiplied by the value that is inside the TV column. Having this, now we need to import our necessary frameworks that will be useful for building the model and measuring the performance of our model. So we need to import the training and testing split. So from sklearn model selection import train test split. Then we need to implement insert, so to import also the linear regression model. So again, from sklearn a linear model we import the linear regression, and also we want the measurement, the metrics, so the measurements, which are the R squared, mean absolute error, mean squared error, and so on. After this, we need to define the variables x and y that we have into the formula. So x is gonna be the independent variable, which is TV. And y is gonna be the sales variable. And now we need to split these two variables into training and testing datasets. So we'll do the following. Xtrain the test size normally goes from 0.2 to 0.4. So I normally select 0.3, which is 30% of the whole dataset. So I will have a testing dataset that is going to be 30%, and training dataset is going to be 70% of the whole dataset that we have. And also we need to set a random variable, random state. In our case, I'm going to put 100, and this is useful so that you are able to replicate the split in the future. So if you don't put the random state, then the split will be done always into a different way. In this way, when you're setting the random state, you're telling, okay, I want the dataset to be split into this way. And this will be repeated always, every time that you run it. After this, now we can just go and define and also fit the model, basically train it. When we are talking about fitting the model, it's we are saying that we want to train the model on the training dataset. So first, let's create the model. And then let's train it. When you see this message, this means that the model has been trained. And now we want to know what are the coefficients A and B from our model. And this we can do it the following way. So we can see that we have the intercept, which is 6.948, and the coefficient is 0.054. So our formula for calculating the sales is going to be like this. Sales equals 6.948 plus 0.0545 times TV. So now let's plot our best fit line with these coefficients to our data sets. And we can do it in the following way. So we will use a scatter plot. Okay, okay, this space should not be here. Okay, so we can see that the blue dots are all the values or all the rows that we have into the training dataset, and the red line is our best fit line that was generated from our linear regression model. Having this calculated, now we can make our prediction on the testing dataset so that we can use it in order to measure our performance on our model. So in order to make a prediction, we do the following way. So I'm calling the model.predict operation, and I'm passing the values of the X tests dataset. Once this is done, we can measure, we can use our measurements. So let's say, let's start with R squared value. So I'm gonna write here R squared value. Let's calculate the R squared value, and for this I need to import the accuracy score. So I'm gonna import accuracy score, and let's call it okay. And now I'm gonna print the R value. So it's gonna be like this. That's okay. So our R squared value is 81.1.10. This means that 81% or 81.1% of the data into our model fits into the regression model. So the rest 19% of the data does not fit into this model. So this means that our score or our performance is 81%, which is not very good. And this should be improved. And this will be improved probably when we will use the multiple linear regression model, because we will have more information on how to build our model. So in meantime, let's also see the rest of the metrics. So for example, the mean absolute error is gonna be then also the mean squared error. I'm gonna change here, and also the root mean squared error, which is simply by np sqrt. Okay. Oops. It should be like this. Matrix mean underscore abs on t. Why? Ah, okay. Here. Yeah, I didn't change this. Okay, so let's print now these values. Mean absolute error is gonna be MAE, then mean squared error, and the root mean squared error. Okay. Okay, we're good. Okay, from the values that we see here, we can see that we have an absolute error of 1.65, mean squared error of 4, and root mean squared error of 2. This is not very good, as we saw also before, because these values here should be closer to 0. The closer to 0, the better our performance of the model is. And in our case, we are outside of by factor of a lot. So in this case, we can simply say that the performance of our model is not very good. So in order to resolve this issue, now let's continue with implementing the multiple linear regression, which maybe will be multiple linear regression, which maybe will help us to improve our performance. And the formula for this type of regression is the following. So y equals a plus b1 x1 plus b2, this is a multiplication here, x2 plus bn minus xn. This means that plus some error, but in our case we will say that there is no error, because this error is calculated by the linear regression, but in our case we can just ignore this because it's going to be very small. And this means that we will have b1 x1, b2 x2, bn xn in our case, we will have 3. We'll have also B3 X3 because we have 3 features. So in our case, we will have the following situation. Sales equals A plus B1 times TV plus B2 times radio plus B3 times newspaper. So, having this information now, let's recreate our X and Y values and then implement again our model. So we'll first define that our X variable is gonna be X variable for our model, not the X independent variable. Now we're speaking about our model. So we define X as the dataset, TV, comma, radio, comma, newspaper. And Y is gonna be again the sales. Now again we need to split our datasets into training and testing datasets. So we can just reuse this code here. Okay, now since we have our split, we can again define our model. So we are defining multiple regression model, which is MLR as multiple regression model. Okay, I'm gonna do it like this. MLR, multiple regression model, equals linear regression. And then I'm gonna train it. Basically, I'm gonna fit it to the training datasets, which are X-train and Y-train. So MRM fit X-train, Y-train. Okay, now it's trained. Now we want to also to print our coefficients. So in order to do that, we will do the following. I'm gonna do print MRM, which is our model, intercept underscore, and then I'm also gonna print out the pairs of the coefficients. So because we have more coefficients, we will have B1, B2 and B3. So we'll need to show for TV, radio and newspaper. We're gonna do it the following way. This is like that. List zip. I'm using zip because I'm gonna call the X variable, this one, in order to take these values here. And the MRM underscore. So we have B1 is gonna be this value here. B2 is gonna be this value here, and B3 is gonna be this value here. Now we will perform our prediction using this model, so that we will be able to see the performance of our new model. And we can do it the following way. So we are creating a new variable, ypred MRM, predict on X test. And now using this prediction, we can do the following thing. The intercept is gonna be always the same. So it's gonna be always used by the model. But we can change these values here because we will modify not these values, but we will change these values here. So TV, radio, and newspaper, because as we remember, we want to see the amount of money that we put into TV marketing, radio marketing, and newspaper marketing. How much will be the sales? So in order to test if our model had some prediction and we'll be able to predict this, we can do the following operation. So we are basically calling the model and we are doing a prediction, so predict, and then we are passing a list of values for these three features. So I'm gonna put like 55 for TV, 60 for, let's say, radio, and 10 for newspaper. And the value for the sales should be 13.958. This is how much sales we should expect if we import this much money into the specific types of marketing. So the last thing that is that has remained to us is to verify if this type of model, so the multiple linear regression model, has improved our performance, because previously, as we saw, it was 81.10%, 81.1%. Now let's see the same value. So I'm gonna just copy it from here, and I just need to change the model. So it's gonna be MRM. Okay, now we have an improvement. Now we have 90% of our values that are included into our model. So this is almost 10% improvement, which is very good. Not the best, but it's quite good. And this will be also improved, but in our exercise, this should be fine. Now let's see also the rest of the measurements. So we're gonna use this. Okay, these are still the same, so I'm just gonna rerun them. And now let's see the values. Okay, there is something wrong here. Okay, I need to change this. Yeah, I need to change this with this. Okay. Okay, we have an improvement. We have an improvement because before we had 1.64, now we have 1.22 for the mean absolute error. For the mean squared error, we have 2.63, before we had 4. And for the root mean squared error, we have 1.62, and before we had the value of 2. So with this, we can conclude our session with implementing the linear regression model on some real-world dataset. And I hope this was helpful, and it's clear how you can use it, how it can be implemented, and how it can be verified and tested using the metrics that we also saw before. And if you have any questions, if you have any doubts, please leave a comment down below, and I will be more than happy to support you and to help you with understanding and resolving your issues. From me, that's all. Thank you very much, and see you in the next one. Bye bye.